Okay, today we'll be going over empty sets and identities. The idea here is that when variables are eliminated while solving the equation, this means you're describing either an empty set due to a false statement, which means it doesn't matter what you plug in, it won't work, there's no solutions. Or when it's eliminated, you get a true statement, which means it doesn't matter what you plug in, it will always be true. Most of what we're used to in class is what we call a conditional statement, where it's sometimes true because there's a limited number of solutions. That being said, if x equals 3, that's a limited number of solutions. It's limited to 1. If x is less than 12, that's a limited number of solutions. Only numbers below 12 work. So knowing these three cases is how we're going to solve some of these problems. Now, if we walk through, we're going to follow the same 4 steps that we've always followed in solving equations. We're going to clean up any parentheses we see by distribution, which means we get a 10x plus 8 is 10x plus 6. We're going to combine like terms, meaning we're going to move all of our x's to one spot, and you already see what's going to happen here. When I subtract my 10x's, they cancel out, and I have a statement that says 8 equals 6, which I know is not true. And if we remember, if it's a false statement, it doesn't matter what I plug into the x variable, this will never work, which means there are no solutions. You can also draw the empty set symbol, and that is our answer. Now, for number 3, if I follow the same 4 steps, I clean up my equation by getting rid of any parentheses. I say 11 plus 2x equals 2x plus 8 plus 3. Now I'm going to move all my x's to one spot. Again, you spot the fact that my x's are going to completely eliminate. I'm left with 11 on the right, 8 plus 3, which is also 11 on the right. This, because the x's are gone, that is a true statement, which means it doesn't matter what I plug in, it will always be true. I have infinite solutions. And so that's that. Now, one of the other things, the other two, is we can follow those same sets and have fractions. Now, fractions aren't a huge deal. I'm going to be showing you a few ways to kind of easily handle them. But however, you're going to notice that as we work, most of them are going to settle themselves out. Now, our first step, again, is to clean up any parentheses that we see. If I distribute that x, I get 5x over 3 minus x is 1/3 plus 2/3 x. Now, there's a couple ways to solve this. What I teach is I suggest if you see a fraction and you don't want to deal with fractions. Now, for the most part, this will settle itself out. If I subtract 2/3 from here, I'll get 3/3, which is x. X minus x, it's gonna disappear. But let me show you a shortcut to dealing with fractions if you don't like dealing with them. All a fraction is saying, let's divide by this. What is the opposite of division? Well, multiplication. So if I multiply each one of these terms by 3, I don't have fractions anymore. So 3 divided by 3 is 1, so I'm 5x. There's nothing divided here, so that gets multiplied by 3. 3 divided by 3 is 1, so 1 times 1 is 1. 3 divided by 3 is 1, 1 times 2 is 2. I combine terms on the left. I'm left with 2x equals 1 plus 2x. And you see again what's going to happen here. When I subtract my 2x, they cancel out and I have 0 equals 1, which I know again, that is a non-true statement. 0 does not equal 1, therefore there are no solutions here. One more. Here, I'm going to clean both of these parentheses up at the same time. So when I distribute this, 7 divided by 7 is 1. 1 times 5 is 5. Half of 10 is 5. Half of 4 is 2. I'm going to combine these two together. 5 plus 2x equals 5 plus 2x. Again, when I subtract my 2x, they go away, and I end up with a statement like 5 equals 5, which is true all the times. So I'm going to say this is infinite solutions. Awesome. And I've got 3 problems down here that kind of highlight clearing of the fraction. And there's 2 ways you can do it. You can either clear one fraction at a time, or you can find the least common multiple and do it all at once. So if I look at number 9, I have a divide by 5 and a divide by 10. I know the least common multiple between 5 and 10 is 10. So I'm going to multiply the entire equation by 10. 10 divided by 5 is 2. So let's multiply the top by 2. 10 divided by 10 is 1. Let's multiply the top by 1. 10 divided by 5 is 2. Let's multiply the top by 2. And see, it's as easy as that. Got rid of the fraction entirely. Negative d is equal to 2, which means d is equal to negative 2. Do the same thing over here. I'm going to look for a least common multiple between 3 and 12, and 3 in essence. But the least common multiple between 3 and 12 is 12. So I'm going to take 12 divided by 3 is 4, and multiply that by 4. 12 divided by 12 is 1, multiply that by 1. 12 divided by 3 is 4, multiply that by 4. And then I go ahead and solve it. There we go. That's how to clear a fraction. Okay, so today we're going to be graphing a line using slope-intercept form. Now, this form, regardless of whether or not you remember how to use it, I'm going to show you how to graph any line assuming that you've forgotten all the steps. But the whole point of graphing a line is we want to visually notice details that may not be obvious by looking at the equation itself. So we want to be able to visualize what's going on with this relationship between an x and y in a way that might make more sense than just reading it. So let's assume, to start out, that you do not know this is a line. You actually don't know what shape this is. Whenever you encounter a scenario like that, what you're going to do is you're going to create an XY table, and you're just going to plug in a few values. Now, my table is centered around 0, so I'm going to plug in some values centered around 0, maybe some to the left, and maybe some to the right. And I'm just going to plug them in and see what I get, see what shape it makes. So if I plug in 0, 0 times 2 is 0, plus 1 is 1. And I'm going to plug in some other points. If I plug in 1, I get 2 plus 1 is 3. If I plug in 2, I get 4 plus 1 is 5. And if I plug in the negative values, I'm going to get a negative 1. If I plug in a negative 2, I get negative 4 plus 1 is negative 3. So I get those aspects. Now, the other thing that we get, especially when we're reviewing how to graph, is, okay, how do I plot these points? Well, if we remember that for x, if it's a negative number, it's left. If it's a positive number, it's to the right. And for y, if it's a negative number, we know it's down. And for a positive number, we know we're going up. So my first point on this graph is going to be 0, 1, meaning no left or right, but I go up 1. And I plot a point right there. I go to the right 1 and up 3. Right 1, up 3. I go right 2, up 5. So 1, 2, 1, 2, 3, 4, 5. Likewise with the negative values, this means I go to the left and then I go down. So I go left 1, down 1. The next one I go left 2, down 3. Another common mistake that's made is that students will plot a singular point and then move up 1 and over 3 from that point, or I guess right 1, up 3 from that point. It's not the way we want to do it, because remember, all of these are measured in relation to the origin or the center of the graph. Left and right, up and down from the center. Once we've gotten all those points together, we're going to go ahead and we're going to connect them with a straight line. We put arrows on the end to show that the line goes on indefinitely, and boom, we're done. If you want to be real fancy, you're going to label your line. Y equals 2x plus 1. Awesome. Let's do another one. For this one, we're actually going to, instead of creating a table, we're going to interpret slope-intercept form. And if we interpret slope-intercept form, that means that we're going to have to realize that this equation is in the form of y equals mx plus b. M being the slope, and b being the y-intercept. Now, the y-intercept is going to tell us where we start. And in this case, we're going to start at -1. Remember, y-axis is the up-down axis. So we're going to start at -1 on the y-axis. The number in front of x is going to tell us our slope. I know my slope is going to be read as rise over run. So if I have a rise of 1 and a run of 2, I know I'm going to go up 1 and over 2, up 1 and over 2. I don't need to actually create a table because I know how to move from point to point to point, and I'm creating my line as I go. Now, can I go in the opposite direction? Well, it looks like if I'm going up and to the right, wouldn't it make sense that I should be going down and to the left? Well, how do I convert 1 over 2 into something that's going down? Well, down and left would mean a -1 over -2. And yes, I can actually do that. Because what is a negative divided by a negative yield? Well, these are all equivalent expressions, so we can either go up to the right or down and to the left. Oh, and I have my graph. And if I want to be real fancy, I'll go ahead and I'll label it 1/2 x minus 1. Awesome. Let's do one more of those. Now, this time I have a negative slope, and I'm also missing my y-intercept. I don't have anything written out here. So what I'm going to notice is that if nothing is written out here, I'm going to assume that it is a 0. Because if I add 0, I'm not actually going to write this. So I know that my y-intercept is at 0. 0 on the y-axis. My next thing is I know my slope, my rise over run, is -2. Well, that's not a fraction, so I know I'm going down 2, but how far am I going over? Well, any whole number is assumed to be over 1. Now, it doesn't matter if you put your negative up top or on the bottom, because let's take a look at what this is. If I reduce a negative divided by a positive, I'm going to get a -2. What is a positive divided by a negative? Also a -2. They both reduce down, so it doesn't matter where you put the negative, as long as you put it in one or the other. Now, that's to say, what is a -2 over -1? Well, that reduces down to a +2, which we know we don't want. So you can either put it in the top or in the bottom, but you can't put it in both because that changes the sign of the slope. Let's go ahead and start at 0. Let's go down 2 and over 1. We're following this rise over run. And to move backwards, we're just going to look at up 2, back 1. Up 2, back 1. And if I'm real fancy, I'll label my line. Awesome. And so what happens if instead of graphing in slope-intercept form, we have something that we have to convert to slope-intercept form? Well, that's no more difficult than what we had. We just need to isolate our y value. So I want to isolate that variable. So I'm going to first get rid of my 2x, which means I have a 5y is 2x plus 12. The next thing that I'm going to do is I'm going to get rid of my coefficient by dividing everything on both sides by 5, which means y equals 2/5 x plus 12 over 5. Now I'm in slope-intercept form. But I know 12 divided by 5 is going to be roughly, let's say, 2.4. And it's actually exactly 2.4, so I can go ahead and straighten out those equal signs. So even though it's a fraction, that's how we're going to keep it, because we don't know the units. We could write it as a decimal so that we know where on this chart to start. So if I start at 2.4, that's going to be up 1, 2, almost halfway on the y-axis. How I move from there is I go up 2 over 5. So I go 1, 2 over 5. Now 2/5 is equal to -2 over -5, which means I can also go down 2 and back 5. And we notice that that is also in line with what we're seeing. So that when we graph it, it's a continuous straight line. I'm going to be fancy and I'm going to label my graph. Y equals 2/5 x plus 12/5. Awesome. And so the next two are going to be the same process. We're going to isolate the y by following the steps of solving any equation, and then we're going to graph it. So my first step in solving any equation is to, now we can work with the fraction, but again, the method that I'm going to be showing here is how to get rid of a fraction, because most of you don't like working with them. Now you can if you want, it's not a big deal. But for this one, I'm going to go ahead and multiply both sides by 9. So I get 9x on the left, and because this is all one term, the 9's cancel out. I'm left with 5, y minus 32. I'm going to go ahead and I'm going to distribute that 5. So 9x equals 5y minus 160. And now I'm at the same point that I was before. I isolate the y by getting rid of the 160. So I have 9x plus 160. And then I get rid of the thing that's multiplied by y by dividing both sides by 5. And that 160 divided by 5 reduces down to 32. And so I get my equation. Now this one in 32, I don't actually have 32 blocks on my y-axis. So I'm going to do something, it's called compressing the graph, and I'm going to make each y, that's an s if you believe me, is going to be 10 units. So instead of going up by 1, I'm going up by 10, by 20, by 30, by 40. And I can make this whatever I want. If I want to make it 14s, I can make it 14s. If I want to make it 12s, I can make it 12s. That is completely up to us as the creator of the graph as to what we best see fit to visually display what we're doing here. Because remember, a graph is so that we can visually see what's going on. So whatever scale you want is the scale that you use. I'm going to keep it consistent and make my x's also by 10s. And so I know I'm going to start at 32. So 10, 20, 30, 32-ish. And I know I'm going to go up by 9 and over by 5. So almost a full block and then half a block. So almost a full block and over half a block. Almost a full block and over half a block. And I can do that each time. So I'm subtracting 9 each time I'm going down. When I went to the right, I'm adding. So 32 became 41, 41 became 50. 32 the other direction, I'm subtracting 9, is going to be 23. I move over half a block. Then I'm going to be at 14. Move over half a block. Then I'm going to be at 5. Then I'm going to be at -4, -13, -22, -31, nope, -31, and 40. Ignore that. And we notice that this is a straight line. And conveniently, I already have my label right here. Awesome. So we're just going with a rise over a run from that point. Now, you might have asked yourself, that was really awkward counting by 9s and moving over by 5s when I have a 10 and 10 scale. So again, we have another trick that we could possibly use on this one. So let's go ahead and let's solve this one real fast. I'm going to combine my y's because I see that I have a y over here and a y over here. So I'm going to move my y's both to the right so they remain positive. So 15x minus 2 equals x plus 11y. Next, I'm going to move my x to the left, which means that I have 14x minus 2 is 11y. My last step is I'm going to divide everything by 11. So I get 14 11ths x minus 2 11ths equals y. That's the expression that I want. So I need to know where to start. So 2 11ths is roughly 0.18. I'm going to start, when it's a negative, just below 0, because this is not very far below 0. And like I said, this was a little awkward, counting by 10s and counting by 10s when my scale in my movement is my 9s and 5s. So this time, why don't I make my vertical scale for my rise? If I'm going up by 14 each time, why don't I make each block worth 14? If I'm moving over by 11, why don't I make each block worth 11 on the left? So now to move up by 14, I move up to here. To move over by 11, I move over. I'm going up a block over a block. So boom, that's my graph. I go down a block over a block. And that was a lot easier. Even have my label. Then trying to count, well, what is 9 on this scale? Can you do that? Yes, we can do that like we did the problem up here. Can we manipulate the graph so that the scale reflects our slope? We can. Now this trick only works for a single line. If I have 2 lines, I'm going to have to end up picking some arbitrary scale. But for right now, enjoy a little shortcut, and that's all we got. So today we're going to be graphing a line using standard form. Now this is different than what we did yesterday where we converted it to slope-intercept form and graphed. Today we're going to be graphing using the X and Y intercepts. Does that mean that we can't use slope-intercept form? Absolutely not. You can still use this format and graph a line. However, we're going to be using the X and Y intercepts because we're going to see this method being used in things like quadratics and polynomials, because X intercepts and Y intercepts are going to be important points on graphs. But because we're still dealing with lines, you can still get away with using both. So let's go ahead and get started. Now, we know that our X intercept is where it crosses the X axis, which means there is no vertical motion. It is at the 0 part, which means there is no height. The Y is equal to 0. So what I'm going to do is say 4x plus 0 for my Y equals 0 and solve the equation from here. Well, I know that 0 cancels out. I have 4x equals 0, which means x equals 0. So I'm going to put a point right here in the center of my graph. The next thing that I'm going to do is I'm going to find my y-intercept. And I'm going to ask, where does it intercept my graph on the vertical line? That means there's no left or right motion, which means my width is 0 in this case. So I'm going to plug in 4 times a width of 0 plus y is equal to 0. Well, I know that cancels out, so I have y is equal to 0. So my y-intercept is also right here. So what we notice is that if we have a case where both intercepts are at 0, we have to find another method, either by using a table or by converting this using slope-intercept form. So let's take a look at what would happen. To subtract my 4x, I get y equals negative 4x. Which means my slope is down 1, 2, 3, 4, and over by 1. Or if I put the negative on the other part, it's positive 4 over a negative 1. And I'm going to connect those 2 points with a line. I'm going to label it for x plus y equals 0. So we see sometimes this method doesn't work if both intercepts are on top of each other, because through any 2 points exists a line. What happens if both points are on top of each other? Well, I'm not graphing on the z-axis, I'm graphing on the xy axis. Let's take a look at the next one. In this case, when I'm dealing with the x-intercept, I want my y to be 0. When I'm dealing with the horizontal line, I want no height in the graph. So I'm going to deal with x plus a 0 is equal to -3. So what I know is that the 0 cancels out. I have x equals -3. So I put my point right there. Now for my y-intercept, this is where I want no width. So I don't want to move left or right. I just want to move up or down on the y-axis. So I'm going to plug in a 0 for x. So I have 0 plus y is -3. That cancels out. My y is -3. Now, unlike the first one where they were both 0, that's at the same point on the graph. If I have a -3 and a -3 for x and y, those are at different points on our graph. So we have the ability to connect those 2 points with a straight line, not requiring an extra dimension. I'm going to put my line, I'm going to label it x plus y equals -3, and I'm going to box that up so I know which line that is. If I have something like this, where I'm dealing with y is equal to -2, well, if we remember from yesterday, we said that if we've eliminated the variable, we're looking at either a true or untrue statement. So here, if I ask if x equals 2, does y equal -2? Yes. If I say, does x equal 0, does y equal -2? Well, yes. If I say, if x equals -pi over e, does y equal -2? Yes. So what it sounds like is it sounds like x has infinite solutions by the appearances because x doesn't matter. But when I actually graph this at -2, I know at x equals 2, y is still -2, and at x equals all of these values, I get a horizontal line. So I know that these aren't solutions per se, but they fit in the graph because they have no bearing. So let's take a look at another one. In this case, I have x equals -1/2, which means that I'm going to put my intercept at -1/2. And I'm going to ask myself, because I have no y, can y equal 5? Well, yeah. Can y equal 100? Well, yeah. Can y equal -infinity? Also yes. So it sounds like that y has infinite solutions, which means that it is a completely vertical line. So we know that this does not matter as long as we've eliminated it from the equation. So let's have something with a little bit more of a challenge on it. So with these values, I know to find my x-intercept, I need to be able to plug in a height of 0 or a y of 0, which means I have 18x plus 2 times my 0 value, which is going to end up canceling out. I'll have 18x equals 8. If I divide both by 18, I get x equals 8 over 18, or 4 over 9, which that's just about a half. If I want to find my y-intercept, I'm going to plug in a 0 width, or when I write out the equation, 18 times 0 plus 2y equals 8. In this case, it's a little easier to work because it's going to end up being a whole number. Y is equal to 4. So if I have x of 4/9, which is just about a half, and y is equal to 1, 2, 3, 4, I can connect those points with a straight line. And I'm going to label it 18x plus 2y equals 8. Now many of you might have said, hey, I can reduce that. And I could reduce this and I would get the same 2 points, so I don't view it as 100% a necessary step, but it is something that might make your life a little easier. So the last one, if I look at number 11, I have the general form of a standard form of a line, ax plus by equals c. I gave you an a, a b, and a c value. So what I'm going to do is I'm going to plug in my a of 6, so 6x, plug in my b of -9 minus 9y, and plug in my c of 3. Now I can solve this. And just to see that reduction doesn't have any effect on the final outcome, what I'm going to do is I've noticed that 3, 6, and 9 are all divisible by 3. So I'm going to reduce this to a 2x minus 3y equals 1. And I know this because I can take the entire equation and multiply it by 1/3 or divide it by 3. So here we go. I have my X intercept, which means I have a 0 height. So I have 6x minus 9 times a 0 height, which will eventually cancel out. 6x equals 3, which means x equals 3/6, or 1/2. For my y-intercept, I know I need a 0 width, which means my x is going to be 0. So I'm going to plug in 6 times 0 minus 9y equals 3. That's going to cancel out. So I'm left with -9y equals 3. And if I divide those both out, I have y equals -3/9 or -1/3. And we notice that if I use the original equation, I'll get 1/2 and -1/3. If I use this equation and I cover up and say, okay, if I plug in y equals 0, that's going to be 1/2. If I plug in x equals 0 and that cancels out, that's still going to be -1/3. So it doesn't matter if you use the original or the simplified version, which is why we kind of skipped it over. The only issue that we see right here is if I plug in a 1/2 and a -1/3, that's going to be a very difficult, accurate line to draw. So what I'm going to do is I'm going to expand my horizons a little bit and zoom in on this graph, which means I'm going to make my x's by 0.1. I'm going to make them tenths. I'm going to do the same to my y's. Each block is no longer 1 unit, it's 1/10 of a unit, which means I need 10 blocks to have 1 unit, which is going to allow me for my x of 1, 2, 3, 4, 0.5, and my y of -0.3 repeating. And simply by zooming in on the graph, it allows me to get a much more accurate example of what that line looks like. So I have a 6x minus 9y equals 3. Boom, and there we go. So today we're going to be graphing an inequality. Now this is just like what we've been doing where we're graphing a line. The only thing is when we graph the line, in this case it's going to be a border. We're either going to be shading above or below the line. And our line itself is going to be saying, hey, this is the starting point or this is the ending point. And the way we're going to tell that is if we have a less than or greater than, dotted lines, because our line itself is not included in the graph. If I have a less than or equal to or greater than or equal to, that means it's going to be a solid line. It's going to be part of the solution set. So I'll go ahead and do that. The next thing is we're going to test a point on either side to see if the result is a true statement. And we always shade the side of true statements because we always want truth to be part of our solution sets. And I'm actually going to show you another method that might help you out a little more than that. So let's take a look at the first one. This one's already in slope-intercept form. So I know the fact that we're going to start at the number of 4. I'm actually going to do this in a different color so we can see it a little better. Apparently blue's not the best. And I'm gonna move, because my slope right here is a -3/1. So I have the choice to put the negative on the top and make it a -3 over a +1, or a +3 over a -1, both of which reduce down to a -3. So I can either go down 1, 2, 3 and over 1, or let's say there wasn't room on this end of the graph, I could go up 3 and back 1. Seeing as I don't need to go in this direction, this should suffice. So let's go ahead. And if we notice, my line's not exactly accurate, but it's going to be a solid line because I have this right here, solid. The next thing I'm going to do is I need to test a point on either side to see if the statement's true. So what I'm going to test is I'm going to test a point right here to see if this is a true statement. 0, 0. So if I plug in 0 into my equation, 0 for y and 0 for x, if it's to be included in my graph, this must be true. So if I plug this in, -3 times 0 is 0, and 0 plus 4 is 4. Is 0 less than 4? Yes. So if that is true, I know I'm going to shade the side with my point because all the other points, that is true, it checks out. All the other points that I could have tested are also all going to be true, which means that my graph is going to be shaded on that side of the graph. Let's try another one. Now in the next one, I notice in this case, it's going to be a dotted line because I don't have the equal to sign included in my inequality. I'm going to start at -3/4, which is not quite a whole. So I'm going to start right about right here. And from there, I'm going to move up 1 and over 2. So up 1 and over 2. And if we notice, I'm not on an intersection because I started at -3/4. So I'm going to stay, should have drawn a little farther low, but I'm going to stay in between those. And in this case, because I want a dotted line, I'm going to pick my pen up several times as I'm drawing this. There we go. That means the points on my line are not part of my set, only the points beside it. Okay. And so I'm going to test a point. Now, typically, I don't test a point this close to the line. You want to pick a point that's much farther away. But 0, 0 is generally a good point to try out because we know 0 is above that point, so I know it's on this part of the graph. 0 is definitely not over here, so when I try it out, let's see what we get. So I get 1/2 minus 3/4. If I plug in 0 for my y and 0 for my x, these cancel out, so 0 is greater than 0 minus 3/4. Is 0 bigger than -3/4? Yes, that is true, which means I'm going to shade the side with that point because that point, quite literally, checks out. If I'd happen to pick a point somewhere else, I'd get an untrue statement. So just to try that out, let's try this point of -5 or 5, -5. If I were to plug that into my equation, I should get an untrue statement, which means I don't shade this side. Let's try it. So if I have a 1/2 minus 3/4, -5, 5. Okay, so what I've got right here is I have is -5 greater than 5/2 minus 3/4. If I change that into fourths, that's going to be -5 is greater than 10/4 minus 3/4. So -5 is greater than 7/4. So first off, I don't really care what the fraction is. A negative is not bigger than a positive. So this is going to be a false statement, which means I do not shade this side of the graph. I have to shade the other side. So no matter which side you test, if it's true, shade with the point. If it's false, shade the other side. Let's try one that's not in standard form. Now, many of you will convert this to standard form, and that works. What we're going to do here is I'm going to show you how to test the X and Y intercepts. So if I have an X intercept, I know I need a 0 height, which means my Y must be 0. To find my Y intercept, I need a 0 width, which means my X needs to be 0. So let's see what we get. So if I have 2x plus blank is 4, 2 blank plus y is less than 4. So what I'm going to do in each case is I'm going to plug in a 0 for the y, and we're going to plug in a 0 for the x. So I know that that's zeroed out, so 2x is less than 4. If I divide both sides by 2, x is less than 2. So like I said, this is kind of a cheaty way. If I have a 2, I know my x is less than, I know I'm going to be shading to the left, because that's where my lesser values are. If I solve for y is less than 4, I'm going to go put a point at 4. I know I'm going to be shading down, because that's where my lesser values are. And if you notice, let's connect this with a dotted line. They're both pointing to the same side of the line. They're both pointing to this side. And so what I've done with this method is not only have I found the points I need to graph, at the same time I have found the sides I need to shade. I don't even need to test the point right here. I could, if I wanted to, I could test the point 0, 0, but it's unnecessary at this point. So if I tested 2 times 0 plus 0 is less than 4. I tried to plug it in. I know that cancels, that cancels. Is 0 less than 4? Yes, that is true, which means that I would, in fact, shade this side. But I didn't need to, because I already knew, based off the y-intercept and based off the x-intercept, that I was shading that part of the graph. So let's do a few more just like that. If I have something like this, I'm going to test the x-intercept, which means I need a 0 height, and the y-intercept, which means I need a 0x. So if I plug that in, I know if I have a y of 0, I'm going to cover up my y and say, okay, 2x is less than -3. And to find my x of 0, I'm going to cover this up and say, okay, 2y is less than or equal to -3. And then I just solve these. Divide each side by 2. X is less than or equal to -3 halves. And on this one, divide by 2. Y is less than or equal to -3 halves. So what I've got is I have my -3 halves. It's in between 1 and 2. My x is at -3 halves. It's in between -1 and 2. And I know it's less than or equal to, which means, I should have done this in a different color, but oh well. Less than and less than. If I were to connect them with a line, I notice that both of them are pointing on the same side. That lets me know that I've done my math correct. I know which side I need to shade. So let's assume on this one, we're going to try this one. Let's say we miss one of these. How will that look? How will we know to go back and check our work? Let's see. So in this case, I've got to do a little bit of rearranging. I've got to move this y over, which is going to give me a 4y. I also have to move this x over. So both those go away. And I'll have a 4x. Oh, no, it's a negative 2. Negative 2x. Let me rewrite that. Negative 2x plus 4y is less than 8. So let's say that I screwed up on one of these. And when I'm finding my x-intercept with a y of 0 and my y-intercept of an x of 0, I miss one of the signs. What would that look like? Well, my y is equal to 0, if you believe that's actually what that says right there. That means that I don't have a y term. I just have a negative 2x is less than 8. This one, if my x is 0, I just have a 4y is less than 8. So I think you might see where I'm going with this. We know that when we divide by a negative number, we flip the sign, so negative 4. On this, if I divide by 4, I get y is less than 2. So if we didn't notice that we flipped the sign, let's see what would happen. Well, if x is greater than negative 4, I know that I'm shading to the right. But if I didn't catch the sign flip, I would have inadvertently said, hey, we need to shade to the left, which we know this is not true. So I'm going to do it in red so we can tell the difference. Y is less than 2, which means I shade down because that's where my lesser values are. And I'm going to connect this point with a dotted line. So one of the reasons why I like the intercept method is because it allows you to check your work. If I didn't catch the sign flip, this would be saying shade above the line, and this would be shading below the line. I'd be like, okay, which way do I shade? I don't know. But because I know that they have to be pointing in the same direction, I know to go back and say, oh, I divided by a negative. That must mean the sign flips. Oh, now they're pointing in the same direction. So now I know that it's actually this side of the graph. Bingo. And so let's do the last one. Now the last one just says, hey, I'm plugging in an A value where I see my A. I'm plugging in a B value where I see my B, and a C value where I see my C. So I get a 4x minus 12y is less than or equal to 20. Let's go ahead and knock this out. X-intercept of y of 0, my y-intercept of x of 0. So I know if my y is 0, I'm going to cover up my y term. 4x is less than or equal to 20. And for my x of 0, I'm going to cover up my x term. 12y is less than or equal to 20. We know there's going to be a sign change because of that negative coefficient. So if we're using this method and we don't notice that, we'll notice that we're conflicting ourselves. But we're going to catch that ahead of time because we're good like that. If I divide each side by 4, I get a point at 5. Divide each side by negative 12. Flip the sign. 20 over 12, I know I can reduce that both by 4. So negative 5 thirds. So let's go put a point at 5. Less than. Negative 5 thirds, which is almost negative 2. And it's greater than. Which means I shade up and to the left. I'm going to draw a solid line because I have the line included. And so what I see is that they're both saying shade above or shade to the left, and luckily I have an above and to the left side. And there we go.